Okay, so we're going to continue dealing with trigonometry and that we're going to be utilizing right triangles, and we're still going to think about putting those right triangles on the coordinate plane, but we're not necessarily always going to assume that those right triangles fit inside of the unit circle today. So what we're going to be able to do after this lesson is construct a right triangle in the coordinate plane that intersects a given point. So you're going to be told a point that it intersects, and it intersects the origin, and its right angle is always going to be on the x-axis. So it's going to be like the triangles that we drew in class today. I can evaluate a given trig function for an unknown angle of a right triangle using known side lengths. And this just goes back to basic trigonometry and the things that you should remember from geometry. All right, so what we're going to start with is just by sketching a coordinate plane. And then we're going to plot the point A, which is given by the coordinates -4, 6. So I'm going to do that now. All right, so now that we have the point A graphed, and it's an informal graph, right? It's not perfect, but I can tell that that point is at an x-coordinate of -4 and a y-coordinate of 6. And in the next part of this question, I'm asked to find the exact value of sine of theta if theta is an angle in standard position and its terminal side passed through point A. So this goes back to what we just learned about putting right triangles on this coordinate plane. What I'm going to do is I'm going to draw a right triangle, again, that starts from the origin and ends at that point. That's the hypotenuse of the right triangle. And it always comes back down and sits on the x-axis. So there's my right triangle. So what do I know about this right triangle right now? Well, I know that this side length here is 6, and this side length here is 4. Those are important pieces of information to have in mind. So if theta is an angle in standard position, we need to find the exact value of sine of theta. And so here's what that means. Theta is this angle. And an angle in standard position is always made from the x-axis right here, the positive x-axis. We always start from there, and we always start moving counterclockwise. So this is theta. And I want to find sine of theta. So this is why we need this right triangle that we just drew. As it turns out, we can use the reference angle to help us do that. So rather than using that standard angle theta, we can use this reference angle theta and calculate sine of that angle. And all we'll need to account for is the sine of our answer. And we'll discuss more about what that means when we finish. Okay, so what I'm going to do now is change what I'm thinking about. I'm not going to think about sine of the standard angle. I'm going to now think about sine of the reference angle instead. Okay. So what is sine of theta then? Well, I know about sine, that sine of any angle is proportional to the opposite side of the right triangle divided by the hypotenuse of the right triangle that angle is within. So what I've done is taken this question and made it about a triangle, which I can do. So I just need to know what the lengths are of the opposite side of this right triangle and the hypotenuse side of this right triangle. And I'm fortunate that I do know one of those. I know that the opposite side is 6, but I don't know right now what the length of the hypotenuse is. So I'm going to have to do some work to figure that out. All right, so over here, I'll go ahead and do a squared plus b squared equals c squared. I know that I've got a 4 squared and a 6 squared. Got to know what the hypotenuse is. 16 plus 36 equals c squared. 52 equals c squared. And I can simplify that when I take the square root of 52. There is a perfect square that is a factor of 52, and it's 4. So I'm just going to show that what I could do here is I could write this as the square root of 4 times the square root of 13. That's the same thing as the square root of 52, which leaves me with 2 radical 13 for side length C. So now I can put that there, remind myself that I do know all lengths of the triangle. And so sine of this reference angle is going to equal 6 over 2 radical 13. And that's the proportion of those sides. Okay, I can simplify this a little bit. I can factor out a 2. All right. And as we saw, we don't want to leave these with a radical in the denominator, so I'm going to choose to multiply this by the square root of 13 over the square root of 13, and that's going to leave me with 3 radical 13 over 13. And that is our final answer, and turns out that is the value of sine of this angle. It is important to remember, however, that this is the angle in standard position and this is the reference angle. And we just did all this using the reference angle. So far, as it turns out, whenever you evaluate sine or cosine of the reference angle, you will get the same thing as if you evaluate sine or cosine of the angle in standard position. We will see situations in the future where this is not the case, and we're going to discuss why that is, but in this case, they are the same. Okay, so don't think of this as a rule that I'm asking you to understand blindly. We are going to break this rule and we're going to see how it is broken. But for now, we're going to stick with you using reference angles to evaluate angles in standard position. The other point that I want to make here is that this is not, and I want to remind you, it's not in the unit circle. The unit circle is a circle with a radius of 1. This hypotenuse is much, much longer than 1. And if, in fact, we look at where 1 would be, this is 1 in the x direction and 1 in the y direction. If I wanted to put my unit circle on here, it would be like here. So this triangle is well beyond the unit circle. We're not staying within the unit circle with situations like this necessarily, but it will become useful to us down the road, especially when we're dealing with those special right triangles. So we want to remember the unit circle. All right, second situation. Now we're given the tangent of theta equals 5 over 13. And we're told that theta terminates in quadrant 3, so we want to determine the value of cosine of theta. So again, take a second, pause the video, draw this situation. Draw a triangle in quadrant 3 and label it according to the information that you've been given. Okay, here's my picture, and I haven't labeled it yet, but just as a reminder, quadrant 1 is over here, this is quadrant 2, this is quadrant 3, and we've got quadrant 4 down here. All right, so I was told that theta terminates in quadrant 3. Again, we start on the x-axis, the positive x-axis, and we go counterclockwise until we get into quadrant 3. This is where theta terminates. So remember, this blue angle that I'm drawing here is my angle in standard position. Then I'm told that tangent of theta equals 5/13. Now I want to think about what I know about tangent. Tangent of any angle is equal to the opposite side of that triangle divided by the adjacent side of that triangle. So if I know that I can draw a triangle in quadrant 3, and again, I'm going to switch from using my standard angle to my reference angle. If I do that, then I'll be saying that the proportion of the opposite side of this triangle to the adjacent side of this triangle is proportional to 5 over 13. So I'm going to label this just like that. I'm going to say that the opposite side of this triangle has to be 5 and the adjacent side has to be 13. Okay. So now we've got a situation where we've got a lot of information about this triangle. Maybe we'll need to know the hypotenuse, maybe we won't. But we're asked to determine the value of cosine of theta. So now I want to think about what I would need from cosine. Cosine is adjacent over hypotenuse. So it turns out that not only will I need the adjacent side, which I have, but I will also need the hypotenuse side. So I'm going to go through the work over here. A squared plus b squared equals c squared. That's 5 squared plus 13 squared equals c squared. 25 plus 169 equals c squared. All right, so 194 is equal to c squared. And as it turns out, the square root of 194 cannot be simplified. So the hypotenuse has a length of radical 194. And now I can evaluate cosine of theta. So cosine of theta must equal the adjacent side, which is 13, divided by the hypotenuse. Again, I don't want to leave radicals in denominators. So I'm going to multiply this whole thing by 1. So I end up with 13 radical 194 over 194. Now we want to think about whether or not what we have here matches the sign of the actual answer. So again, consider that we used the angle in standard position, turned it into a reference angle, and then used that reference angle here. This is a case where we are wrong about this answer if we leave it like this. As it turns out, our final answer should actually be negative, and here's the reason why. In this triangle that we just built, we labeled the sides, but we haven't considered the direction of where this triangle is positioned inside of the coordinate plane at all. If we do that, then we have to acknowledge that this 13 is a negative 13 because it ended up in quadrant 3. So we traveled in the negative x direction to get there. Now it didn't end up mattering, but we also traveled in the negative y direction to get to this point. So if we had operated with those correct signs this whole time, when we used the adjacent side length, it should have probably been negative if we wanted to account for that. And when we do that to the very end, we end up getting a negative divided by a positive, which ends up being a negative number. So cosine of this theta is a little different from cosine of this theta. The only difference is the sign. So we're just going to have to make sure that we look out for that, and we'll come up with a rule that works for just remembering what sign these functions should be within this coordinate plane. But right now I want you to see that the reason that we have to account for the sign is because of the triangle that we drew and where we drew it. So we're going to spend some time practicing this in class. I would encourage you to go back and pause parts of this video that maybe were a little confusing. I know it was a little long, but we're going to practice this tomorrow. So make sure that you're ready to go in class, and I'm happy to answer any questions that you have.